Okay, let's unpack this because I want you to imagine you're driving, say, 70 miles an hour down the highway.
Right, just a normal commute.
Yeah, exactly. And you roll your foot onto the accelerator because you need to pass a truck, right? So you're demanding this sudden, massive surge of power.
Mm-hmm.
And in that specific fraction of a second, just because two processors inside your transmission fail to perfectly share, like a single memory buffer.
Yeah, just a microscopic software glitch.
Right. Because of that, your traction motor tries to violently accelerate, but your generator motor suddenly attempts to apply maximum regenerative braking.
Oh, man.
Yeah. Within 50 milliseconds, the physical driveline of your vehicle is basically trying to spin forward and backward at the exact same time, under thousands of Newton meters of force.
Which is, I mean, that is just a terrifying scenario when you really picture the physical forces involved.
It is, and that's what we're looking at today. We have this massive stack of technical specifications detailing what's called a TMGM torque coordination failure.
Yeah, in hybrid dual motor systems, like the power split systems.
Right. And this isn't, a mechanical wear and tear issue or a belt snaps. This is a microsecond-level synchronization failure where the math literally tears the physical metal apart.
It really does. And if we connect this to the bigger picture, the energy management systems in these dual motor architectures, they're balancing highly, highly volatile forces.
Mm-hmm.
When you operate an architecture like an ECVT, the traction motor or TM, and the generator motor, the GM, they are just doing their own thing in isolation.
Right. They're physically connected.
Exactly. They are mechanically coupled through a planetary gear set, and they're electrically coupled through the exact same high-voltage DC bus.
So they share a brain and a skeleton, basically.
Yeah, that's a good way to put it. And this specific failure carries an ASIL D rating.
An ASIL D, for those who might not know, that's the absolute highest automotive safety integrity level, right?
It is. It means we are squarely in the domain of catastrophic, life-threatening hazards.
Wow.
Because if the torque vectors of those two motors misalign during a high dynamic shift, you aren't just looking at, some strip gear teeth.
Right, it's way worse.
Oh, yeah. You're looking at a transient voltage spike that could literally blow through the isolation boundary of the inverters, or a mechanical locking event that just seizes the wheels while you're going highway speeds.
Seizing the wheels at 70 miles an hour.
Yeah.
Just because of a millisecond math error.
Exactly. Lives are quite literally on the line.
Which means understanding how this system protects itself, it requires understanding exactly how that physical and digital coupling actually breaks down.
Right.
And the engineering documentation we have, it outlines 4 primary root causes for this specific ASIL D failure.
Let's get into them.
So the first one is a pure physical desynchronization. They call it torsional resonance.
Mm-hmm.
We're talking about the elastic deformation of the driveline, because when the internal combustion engine fires up, the GM has to instantly drag it up to idle speed, right?
Right. Well, the TM is already actively driving the wheels.
Exactly. And when that happens under heavy load, those physical steel shafts, they actually twist. They act like torsion springs.
They absolutely act like springs. And that elastic characteristic is exactly where the math starts to break down.
How so?
Well, to counter that natural torsional windup, the power electronics use something called active damping.
Okay.
The software injects this anti-phase torque ripple. It essentially commands the motors to pulse in exact opposition to the mechanical twist of the shaft.
Oh, so it's trying to absorb the kinetic energy of the vibration, like pushing someone on a swing, right?
That's a perfect analogy, yeah.
Yeah.
If you push someone on a swing at the right time, like an anti-phase, you slow them down safely.
Right. You absorb their momentum.
But the critical failure mode here happens in the phase compensator of that damping algorithm.
Mm-hmm.
If the software calculation lags behind the real-world mechanical state by more than 90 degrees,
Uh-oh.
yeah, your negative feedback vector mathematically inverts.
Because at that point, you aren't pushing against the vibration to cancel it out anymore. Your damping pulse arrives so late that you're pushing in the exact same direction as the shaft's natural rebound. You're creating positive feedback.
Exactly. You push the swing at the exact wrong time, and the swing goes completely out of control.
You're injecting these high-frequency torque ripples that multiply the mechanical resonance instead of stopping it.
And then the transmission enters a state of violent, amplifying oscillation. The physical stress on the gear teeth and the rotor shafts themselves, it exceeds their ultimate tensile strengths incredibly quickly.
That's terrifying. That's just a mechanical lag. That's just the first failure mode.
Right, that's just number one. The second root cause happens entirely within the magnetic physics of the motor itself.
The stator, right, electromagnetic distortion,
Mm-hmm.
or double motor cross-saturation.
Yes. So when you demand maximum acceleration, the inverters dump these massive phase currents into the stator windings.
To generate the torque.
Right. But those currents force the electrical steel of the motor core incredibly deep into its non-linear saturation region, on what we call the BH curve.
So it's like the magnetic permeability of the iron core basically just collapses under the extreme load.
Yeah.
Like trying to pour water into a sponge that's already totally soaked.
Mhm.
If the iron can't hold any more magnetic flux, pushing more current into it doesn't give you a linear increase in torque anymore.
Precisely. And the documentation shows that the direct axis and quadrature axis inductances, the LD and LQ values, they experience a sudden drop of 30 to 50%.
50%. That's a massive drop.
It's huge. And that collapse in inductance is the trap. Because the field-oriented control loop, the FOC, it relies on a mathematical model of the motor to calculate the exact current needed for a torque request.
Oh, I see.
So if the FOC algorithm is operating on nominal parameters, assuming the inductances are at their normal values, it completely misunderstands the physical state of the motor.
It's blind to the reality. So the controller asks for, say, 300 Newton meters of torque, calculates the currents based on an unsaturated map, and just fires the inverters.
Right. But because the physical magnetic map has shrunk by half, the motor's actual physical output is entirely different from what the math requested.
So you've got the traction motor operating on this corrupted physical reality, which creates an immediate torque mismatch between the TM and the GM.
Exactly.
And that actually leads perfectly into the third failure mode, which is kind of the bridge between the high voltage physics and the low voltage computer logic.
The noise problem.
Yeah, the DVDT communication desynchronization.
This one is fascinating. The transition to silicon carbide, or CC switches, is the primary driver here.
Right, because they operate at crazy speeds.
Yeah, they're incredibly efficient, precisely because they transition between on and off states in mere nanoseconds. But that speed creates extreme voltage slew rates.
I think the spec said 10 kilovolts per microsecond.
Yes, 10 kilovolts per microsecond. That astronomical rate of change acts on the parasitic capacitances inside the power module.
Because the faster the voltage changes, the more those parasitic capacitances start acting like actual short circuits, right?
Exactly. You're pumping high-frequency common mode noise directly into the cooling loop and the chassis ground.
Wow.
And that ground bounce lifts the reference voltage for the entire logic board.
So if your CAN-FD data lines are relying on a differential voltage to read the ones and zeros, and the ground plane itself suddenly spikes by several volts due to all that electrical noise.
The differential receiver just reads garbage. The common mode spike destroys the signal integrity, and the data frame fails its cyclic redundancy check.
So the packet just gets dropped.
Yep. Now, apply that to our dual motor setup. The vehicle control unit broadcasts this highly synchronized, time-critical torque command to both the TM and GM cores.
Okay, so they both need the command at the exact same time.
Right. But the EMI spike scrambles the frame for the GM, while the TM happens to receive it perfectly.
Oh no, so by the time the GM realizes it missed it, requests a retransmission, and finally gets the new target.
50 milliseconds have already passed.
And in car computer time, 50 milliseconds is an eternity.
It really is. In those 50 milliseconds, the TM is already executing this massive acceleration command, while the GM is still locked into whatever the old command was.
They are completely out of phase, which honestly sounds a lot like the fourth root cause, but that one happens entirely inside the processor itself.
Yeah, the multi-core race conditions, software traffic jams.
Right, so you have this architecture where Core 0 manages the TM and Core 1 manages the GM. And to coordinate, they have to write and read from a shared memory space. They share variables for target torque, rotor angle, all that stuff.
But if they don't share that memory perfectly, you get what's called data tearing.
Wait, data tearing? Is that like, okay, imagine two chefs sharing one recipe card and one chef flips the page while the other is still reading the ingredients.
That is exactly what it's like. It's a time skew issue.
Okay.
The processor is writing a 32-bit number, but it has to do it in two 16-bit chunks.
Yeah.
So if Core 0 writes the high byte of a new torque command, but before it can write the low byte, Core 1 executes a read operation.
Core 1 pulls a Frankenstein number.
Exactly.
Yeah.
It reads the high byte of the new target, but the low byte of the old target. The entire state machine desynchronizes instantly based on corrupted math.
That is wild. So to recap, you have mechanical vibrations mathematically inverting, magnetic fields physically collapsing, electrical noise scrambling the network, and processor cores literally tearing data apart.
It's a miracle these cars drive at all, honestly.
Right. The sheer physics of the environment are actively working to ruin this synchronization. So how on earth does the car's computer catch these invisible errors before the driver even notices?
Well, the functional safety architecture relies on deeply layered, heterogeneous diagnostics. You can't just rely on one check, because whatever electrical noise caused the fault might also blind your diagnostic monitor.
That makes sense. So what's the first line of defense?
The primary gatekeeper is plausibility gating. It's basically a relentless math check based on the conservation of energy.
Okay, comparing the physical DC electrical power being drawn from the battery against the estimated AC mechanical power actually being produced at the wheels.
Exactly. Volts times amps at the input versus torque times angular velocity at the output, minus the calculated thermal and frictional losses.
Right.
What's fascinating here is that the diagnostic software runs this residual calculation every 100 microseconds.
Wow.
And it looks for a mathematical deviation of 15%, or a physical delta of about 50 newton meters between what's commanded and what's estimated.
And the 15% margin, I assume that's to account for just normal real-world efficiency fluctuations, right? Like things getting hot.
Exactly. Inverter switching losses vary with temperature, copper resistance changes.
Yeah.
You can't trip a massive ASIL D fault just because the motor got a little warm.
Right. But if that math is off by more than that 15% for just 10 milliseconds, the system instantly flags a severe failure, the DTC P0A7A code.
Yep. But here's the catch. You can't rely entirely on the main processor to execute that plausibility check.
Why not?
Because if that data tearing we just talked about corrupted the processor's core logic, it might just perfectly validate its own flawed math.
Oh, wow. It marks its own homework and gives itself an A.
Exactly. So that vulnerability is why they use a doer checker, dual-core, lockstep philosophy.
Okay, I read about this. It's asymmetric redundancy, right?
Yeah. One core, the doer, does all the heavy computational lifting, the field-oriented control, the active damping, all the high-frequency switching.
And the checker core.
Checker core is physically isolated and runs a completely different, highly simplified mathematical model based on unbreakable laws of physics, like stator flux conservation.
So it avoids common cause failures by not even trying to do the complex math.
Right. It just looks at whether the doer's requested output mathematically violates the absolute physical limits of the DC bus.
And if it does?
If the checker catches the doer trying to do something unsafe, it doesn't even try to correct the math. It completely bypasses the main core, triggers a hardware interrupt, and directly kills the power to the inverters in under 100 microseconds.
Just pulls the plug. But wait, if the system catches an error while the motor is spinning at like 7,200 RPM, it can't just slam on the brakes or cut power, right? Wouldn't that destroy the transmission anyway?
You are absolutely right. That introduces a massive secondary hazard. If the checker trips at highway speeds, you cannot just transition to an open circuit.
Because the permanent magnets are still spinning inside the motor.
Right, they act as an uncontrolled generator. The back collector motive for the back EMF would easily exceed the voltage rating of the battery contactors.
So letting it freewheel would just pump a massive destructive voltage spike backward into the battery.
Exactly. It would fry the system. So that dictates the fallback strategies or safe states. The system has to grade the fault.
Okay, so for a minor error, like a brief sensor glitch.
For a minor error, it initiates a controlled ramp down. It gently pulls the torque to zero at a strict rate of 1,000 newton meters per second.
So it doesn't just jerk the driveline.
Right. But for a severe fault, like a data tear or a complete communication loss, ramping is way too slow. The window for disaster is too small.
So what does it do?
It triggers a stepwise active short circuit, or ASE.
Okay, but you can't just short all three phases of a motor instantly at highway speeds, right? The mechanical shock would be insane.
It would be devastating. It would snap the rotor shaft or completely shear the motor mounts. That's why it is explicitly stepwise.
How does that work?
The safety controller shorts only 2 of the 3 phases for precisely 1.5 milliseconds.
Oh, so leaving that third phase open momentarily throttles the initial surge.
Exactly. It acts as an inductive buffer to suppress the peak transient torque.
It's essentially slipping the clutch electronically to bleed off the initial shockwave.
That's a great way to visualize it.
Okay.
And then after that 1.5 millisecond cushion, it closes the third phase. This traps all the electrical energy within the stator windings themselves.
So the kinetic energy is dissipated as heat in the copper rather than shooting back into the battery.
Right. It caps the DC bus voltage safely below 720 volt.
But wait, if you short the motor, that creates braking torque. If this happens at low speeds, like under 2,000 RPM, wouldn't that just violently lock the wheels?
It would, which is why the fallback state evaluates rotor speed first. At low speeds, the back EMF is lower than the battery voltage, so there's no risk of an overvoltage spike.
So below 2,000 RPM, it just opens the circuits and lets the motor safely freewheel to a stop?
Precisely. No short circuit required.
Man, catching an error in 60 milliseconds and routing the energy like that is incredible. But in engineering, it's obviously much better to design the system so the error can't physically happen in the first place.
Right, prevention over reaction.
Which brings us to the design failure mode and effects analysis, the DFMEA. How do they idiot-proof this at the blueprint stage?
They systematically target those 4 root causes we talked about. So for the active damping lag, the torsional resonance, you can't wait for a physical sensor to report that the shaft is twisted.
Because by the time the data is processed, you're already lagging.
Exactly. So they implement Kalman shaft observers in the software.
That's a concept from aerospace navigation, isn't it?
It is. It's not just reacting to sensor data. It creates a high-fidelity, virtual kinematic model of the transmission that runs parallel to the physical hardware.
Oh, wow. So it's calculating the twist of the metal before the sensor even feels it?
Yes. By driving the anti-phase damping off this predictive virtual model rather than the delayed physical sensor, they completely eliminate the phase lag.
It keeps the damping perfectly aligned. The notes say it reduces those violent vibrations by over 20 decibels.
It's remarkably effective.
Okay, so what about the software race conditions, the chefs sharing the recipe card?
To solve the data tearing, you have to move the synchronization out of the software's hands entirely.
Oh, really?
Yeah, software likes introduce too much timing jitter, so they enforce it at the hardware level using lock-free double buffering, hardware semaphores.
Basically traffic lights for data.
Exactly. The shared memory space is literally partitioned. Core 0 writes the new variables to a secondary locked buffer, and only when that write operation is 100% complete.
The hardware flips a switch and makes that new buffer the active one for Core 1 to read.
You got it. The cores can physically never interact with the same memory address at the same time. It mathematically eliminates data tearing.
That's brilliant. Here's where it gets really interesting for me, though. The third prevention tackles the magnetic distortion, the inductances dropping when it's under load. You can't just rewrite the physical properties of iron.
No, you can't rewrite it, but you can memorize its flaws.
Okay, how?
They use a 2D LUT, a two-dimensional lookup table hard-coded into the memory. During the design phase, they map exactly how the magnetic field warps under every possible stress level.
So the software isn't relying on a static value. It's constantly checking this map based on the current load, so it knows exactly how warped the motor is before it even asks for torque.
Exactly. But it's not just magnetic stress. When the motor gets up to, say, 150 degrees Celsius, the electrical resistance of the copper windings shoots up too.
Right. Heat changes resistance.
Which would also skew the math. So they pair the lookup table with an RLS algorithm, recursive least squares.
What does that do?
The controller actively injects these tiny high-frequency diagnostic pulses into the power stream and measures the voltage response to actually recalculate the copper's resistance on the fly.
Oh, wow. So it's constantly adapting to the real-time temperature.
Yes. Between the LUT handling the magnets and the RLS handling the heat, they keep the internal math error strictly under 3%.
That's so precise. But none of that math matters if the communication lines get scrambled by all that electrical noise from the fast switches?
Right, the 10 kilovolt per microsecond EMI noise. To bulletproof the comms, they mandate extreme physical layer hardening.
The documentation mentions specialized Class 1 C0G ceramic capacitors. What makes those so special?
The C0G specification is vital because those specific capacitors have a zero temperature coefficient.
Meaning they don't change behavior when they get hot?
Exactly. If you use a normal capacitor, its capacitance drifts wildly as the engine bay heats up. And in a differential signaling system like CNFD, if one data line drifts differently than the other because of a temperature gradient,
you lose your differential balance.
And the moment you lose that balance, all that electrical noise converts straight into data corruption. Using zero drift capacitors ensures the filter remains completely impenetrable no matter how hot it gets.
Okay, so the design is theoretically perfect on a computer screen. But the factory floor doesn't care about schematics.
No, it does not.
If the assembly line introduces a microscopic defect, all this mathematical prevention goes out the window. Which brings us to the process failure mode and effects analysis, the PFMEA. How do they guarantee a perfect build?
At an ASIL D level, you have to treat microscopic defects as latent catastrophic failures. We know a 50-millisecond communication loss causes the motors to desynchronize, right?
Right.
Well, one of the main real-world causes of that is micro-cracking in the solder joints underneath the computer chips.
Because the silicon chip and the circuit board expand and contract at different rates as the car heats up and cools down over the years.
Exactly. It puts massive shear stress on those microscopic solder balls. And if there's even a tiny air bubble, a void trapped inside the solder during manufacturing,
It becomes a weak point, a stress concentrator.
right. Over thousands of heat cycles, a microcrack grows from that void until it severs the connection. Then you hit a pothole, the circuit opens for a millisecond, the data drops, and the torque coordination fails.
Just from a tiny bubble of air. So how do they catch that?
They use 3D automated X-ray inspection, AXI. Every single critical chip gets a volumetric X-ray on the assembly line.
They literally X-ray the solder joints.
Yep. And the limit is incredibly strict. Total voiding area must be under 5%, and a single void cannot exceed 1% of the volume. If a joint has a 1.2% air bubble, the system instantly quarantines the board.
That is insane precision.
It is, but physical connections are just part of it. The next critical step is the EOL-ROL lock, the zero-position self-learning.
Okay, so the physical assembly of the motor always has tiny tolerance variations, right? The magnetic north of the rotor won't perfectly align with the physical 0-degree mark on the sensor.
Exactly. And if the software doesn't know that exact microscopic offset, that whole 2D lookup table we talked about gets applied to the wrong spatial orientation.
Oh, so it would inject power at the wrong angle, which could command torque in the wrong direction.
Precisely. So at the end of the line, the factory physically spins the motor to find its exact magnetic 0 point.
And the ROL lock.
If the car's computer doesn't save that calibration perfectly to its own memory and sync it flawlessly to the manufacturer's cloud database, the factory system physically intercepts the part.
The notes say it literally cannot be given a barcode to leave the factory.
Right. It creates a hard interlock. It cannot proceed without a cryptographically verified zero-position map.
Wow. And then finally, before it leaves, they do a dynamic end-of-line torture test.
Yeah, they don't just gently spin it to see if it works. The factory machine simulates a sudden, wide-open throttle acceleration and then instantly triggers a simulated fault.
They're testing the reaction time on the actual assembly line.
Exactly. The motors have to react in less than 10 milliseconds, and the active damping can't overshoot the target by more than 5 Newton meters. Any lag, any overshoot, and the part is scrapped.
So they design it perfectly and they build it perfectly. But before mass production even starts, the engineers have to try their absolute hardest to destroy the prototype, right? The DVPNR, production validation.
Oh, this is where it gets really fun. They have to prove it can survive the operational life of the vehicle. It starts with the shake and bake.
Sounds intense.
It is. They mount the fully assembled unit to an electrodynamic shaker table and vibrate it violently from 10 hertz up to 2,000 hertz.
While simultaneously baking and freezing it, right?
Yes, cycling the chamber from negative 40 degrees Celsius to positive 125 degrees.
Yeah.
For over 1,000 continuous hours, while fully powered.
And they're looking for even a microsecond voltage drop. But passing that isn't enough, is it?
No. Afterward, they perform a destructive physical analysis. They take the fully functional board, cast it in solid epoxy, slice it cross-sectionally, and put it under a scanning electron microscope.
So they literally cut it apart to look for microscopic fatigue that hasn't even broken the circuit yet.
Exactly. They destroy the survivor to prove it wasn't even close to failing.
That's hardcore. But physical destruction is only half the battle. They also have to test that 100 kilovolt EMI immunity, the electronic battlefield.
Right. They spin the motors at 12,000 RPM, generating maximum internal noise. Then they attack externally.
Using bulk current injection, clamping a probe onto the wires and just blasting it with high-frequency current.
Up to 200 milliamps, directly onto the data lines. They are aggressively trying to exceed those C0G capacitors and corrupt the data.
And at the same time, they're radiating the entire housing with 100 volts per meter of electromagnetic energy.
And the acceptance criteria. 0 degradation. Not a single dropped frame, not a single Newton meter of torque drift. If even one bit flips, it fails.
It just proves the shielding is absolute. But the last phase of validation, I think this is the coolest part. They don't test the hardware. They test the software's ability to safely fail. ASIL fault injection.
Hardware-in-the-loop virtual sabotage.
It's like the Matrix for motor controllers.
It really is. They wire the brain of the car directly into an FPGA supercomputer. It feeds the controller nanosecond accurate data, so the processor genuinely believes it's driving down the highway at 70 miles an hour.
And while the controller is perfectly doing its job, the engineers just reach into the simulation and pull the pin on the grenade.
They deliberately inject the exact failure modes we've been talking about. They corrupt the CAN FD frame. They overwrite the memory map with garbage data. They introduce a 15-millisecond delay to trigger that torsional resonance.
They force the ASIL D condition, and the controller has just 60 milliseconds to realize that its reality just violated the laws of physics.
Exactly. The system measures its reaction down to the microsecond. Did the checker core bypass the doer? Did it execute the 1.5 millisecond two-phase short perfectly before clamping all three phases?
It validates that the electrical suicide pill works flawlessly under the absolute worst-case scenario.
It's just staggering when you step back and look at it all.
It really is. From a 50-millisecond network delay threatening to tear a transmission apart, to the asymmetric math checks, the predictive virtual models, and the factory X-rays hunting for a 1% air bubble in a tiny bead of solder.
The depth of engineering required just to safely put two electric motors on one driveline is immense.
So what does this all mean for the future? Because there's a really fascinating detail at the very end of the source material about how they actually design these tests.
Right, the Python simulation tool.
Yeah. The text mentions that they use advanced Python software to model the electromechanical coupling during these failures.
Because the interactions between the collapsing magnetic field, the electrical noise, and the physical shaft resonance, they're just too deeply entangled to figure out on a whiteboard.
You need a supercomputer just to simulate the edge cases where the safety software might fail, so you can design the safety software's backup plan.
Exactly.
Yeah.
And this raises an important question, I think. As hybrid architectures move to even higher voltages, 800-volt, 1,000-volt systems and computer speeds keep increasing, the timeline for a catastrophic failure is going to compress from milliseconds into microseconds.
Oh, wow. That's true.
Are we rapidly approaching a threshold where the cascading physical and digital effects of a failure simply outpace human intuition entirely?
We're already relying on AI and Python models to tell us exactly how many nanoseconds we have to short-circuit a motor to prevent disaster.
Right. Moving forward, will human engineers just set the safety goals while the AI architecture completely designs, codes, and validates its own mathematical failsafes?
Just locking human comprehension out of the diagnostic loop entirely?
It's entirely possible.
We are building drivetrains so immensely complex that we have to rely on artificial intelligence just to tell us how to keep them from destroying themselves. Something to think about the next time you step on the accelerator. We'll catch you on the next deep dive.